We apologize. Dr. Wong is having some technical difficulties, so I will kick this off. We have with us today Mr. David Broyles to give an introduction to AI and terminology. So over you, David, please, and please feel free to introduce yourself in more detail. Thank you.
All right, thank you very much, Mark. Can everyone hear me okay? Just do an audio check.
I have you loud and clear, David. Visual and audio. Thank you.
Good to go. All right, thank you. Yeah, my name is Dave Broyles. I've been at CNA for nearly 16 years, and I'm the director of our Special Activities and Intelligence program here. We basically do operational work at the operational level work with cyber operations, special operations, and autonomy and AI related issues. When my colleagues mentioned that CNA would be hosting the Connections War Game this year and that the theme was AI, I thought, well, hey, you know, maybe it's a good opportunity to do a little introduction for people that may be a little bit less familiar with some of the terminology in the field. And so you're going to have a whole week-long discussion on wargaming and how it potentially relates to AI. You know, for those of you that might find it useful, to provide some information and background, to provide a reasonable foundation for the rest of the week. Now, I can't make AI experts in 30 minutes, so we're going to go through a lot of material, but the brief that I provided has the notes relatively well filled out with lots of references and links. So please feel free to look at that at your leisure, and you'll see one of the slides as well is designed as a cheat sheet to have a very microscopic size text on the slide to provide a lot of references for definitions and terminology for you to use. So with that, I will attempt to share my screen here and go to our slides. All right, here we go. So we're going to go very fast over the background of AI, and then we'll dip into some of the terminology. We'll talk about some recent examples and some themes to be aware of, just to kind of know in your back pocket. And then we'll close with some thoughts on how to think about applying AI, particularly if, you know, when you're sitting in a game and someone says, hey, let's add AI to this. How are some ways to maybe think about that? So a quick, again, dip into the history. The origins of AI research really goes back to the 40s, and depending on who you talk to, maybe even earlier than that. But the point of this slide is really to show you that we're really working on almost a century worth of really solid research and information on artificial intelligence and the things that are related in this field. So I'm not going to go into a lot of these things, but one thing I just kind of want to point out too is when you talk to people, they'll often talk about these sort of slower periods, sometimes called dark periods. And again, I'm not going to go into the detail of what was happening at the time, but those were just periods where basically research, funding in particular, kind of slowed down, and the theories had kind of hit their limit. And it took time, right? It was a smaller field than it is today. It took time for things to kind of gain momentum again, make some breakthroughs, and push ahead. And so it's just kind of something to keep in mind. We're sort of on like a third push, so to speak, when it comes to all the breakthroughs and things that we're seeing today. So why are we seeing all these breakthroughs now? Well, there's a number of reasons. The two primary ones are basically the increasing availability and prevalence of large amounts of data, thanks in large part to the internet and the connection of computers across the globe and the amounts of information and data that they generate. And also, most importantly, probably the increasing availability of computing power at lower cost. And so the little graph here gives you kind of a depiction over time about how the cost of computation power has been decreasing, or the availability of the power has been increasing. And as an example, just as a reference point, on the right side of the slide, you'll see a little human brain there, roughly about the 1 exaflop, which is 10 to the 18th computing power, so to speak. It's not an exact comparison, but you know, give or take roughly that level. Well, this was achieved, that level of computing was achieved basically in 2018 at the end. This was Lawrence Berkeley National Labs, who was doing modeling on environmental related work. But, you know, just to put it in perspective, they used basically 27,000 graphical processing units to do that work. So we're not talking something that's very readily available to the average organization even. But as time goes on, right, we expect the availability of the computing power and the cost of it to become more accessible. So let's talk about some of the terminology in AI and what's going on. We're going to start with looking at the complexity sciences. That's just kind of a broader picture of what's kind of going on in the area. And then we'll talk more specifically about AI and things like machine learning, and then look at some examples. So this little eye chart is pretty fun on the complexity sciences. Brian Castellani put this together in 2018. The really neat thing about it is when you go on to the web link where it is, everything there is hyperlinked. So if you're curious and just kind of want to look at this later and just explore like what is global network society, you can click on that and you'll get further information, whether it's a wiki page or a researcher's page or some other information. But again, this is just kind of show that there's a lot of work that's been going on for decades in a variety of fields. And that's the real thing about the world of AI. It encompasses a lot of different things that isn't just robotics or making computers smart and machine learning. It includes things like dynamical systems theory and chaos theory, agent-based modeling, big data related stuff, network science, complex systems theory. There's so much that kind of is wrapped around this and is involved with what we're seeing. So it's just something to keep in mind. And these are very active fields of research, which is another important thing to keep in mind. So one of the first things that you'll run into when people talk about what is AI is, of course, there's really no consensus. There's really still no agreed upon definition. And so you'll get kind of a smattering of definitions depending on who you talk to that all kind of hit around the same rough target. But again, because this is still a burgeoning field, lots of people have different views about what exactly makes this, what exactly is the finer point of why, I think AI has this little aspect as opposed to some other, emphasis that someone else wants to make. But again, they all kind of beat around the bush that AI are systems that think like humans and act like humans, and that think rationally and act rationally, and that can act with foresight in any environment in which they're put. And again, just to kind of hammer home the idea about the difficulty of the definitions, that last reference there on the slide, A Modern Approach to Artificial Intelligence by Russell and Norvig, which actually just came out with their 4th edition just a couple months ago. So they have an updated version of that book. But they had at least 8 definitions of what AI was in that one tome. So just to give you an idea. It kind of helps. So there's many ways to slice and dice the large amounts of things that are going on in research in this area. And this is one way to look at how kind of deep learning, machine learning, and artificial intelligence are related to each other. And you can see the sort of nesting there, right? Machine learning is a subset of AI, and deep learning is a subset of, is a type of machine learning. Well, back in 2015, Pedro Domingo put together what he called the 5 tribes of AI. And this was kind of an attempt to categorize where many of the researchers were putting their focus. So again, because there's not necessarily one definition of, what is AI, what's the final bullseye target, there's lots of ideas from researchers on what are the important components that we need to be paying attention to in order to achieve this ability to have a non-biological intelligence. And so again, you can see the 5 different groups that he identified there, and they're color coded kind of about where they sort of focus in that hierarchy of AI and machine learning and deep learning. So we're not going to go into details of this. This is more a way to highlight the fact that, again, lots of different researchers focusing on different pieces of this enormous puzzle and trying to make sense of how it all fits together. And again, just for your reference, on the right side there, there's a little laundry list of terms that are sort of relevant in this area. And if you're curious about those, you can always like Google stuff and find out some more information on them. So typically, when talking about AI, people will very quickly get to the idea of narrow AI versus general AI. And the basic bottom line is that narrow AI refers to the idea of a system designed to handle a very specific problem or a task. And it's important to point out that basically everything that we've seen to date, not basically, but yes, everything that we've seen to date is an example of narrow AI. There is no known example of general AI at this point, with general AI being a system that can handle any task that is thrown at it. These systems, right, they're designed to learn from data and improve performance on any given task. And the words that you'll usually hear in this arena to enable machines to learn deals with the type, how basically are you going to give that algorithm data, and how are you going to get it to learn? And the terms that you'll typically hear are supervised, unsupervised, and reinforcement. Now, there's many other terms that are out there. Some are a mix and a hybrid, but these kind of are the basic ones. And you can see the definitions there. Supervised refers to labeled data. In other words, I've got 10,000 photos of dogs, and I put a little hashtag label on that photo that says dog. And then I have maybe 10,000 photos of cats, and I have a little hashtag label that says cat. And that is my way of labeling the data so that when I go and try to train my algorithm to distinguish dogs from cats, I'm giving it a bunch of stuff to learn from, to train on, and I've provided the answers. Unsupervised learning is basically when you don't have labels on your data. And this is typically used for things more like, say, seismology or other things where basically you've got maybe some time series data or something else, and you're going to feed the information to an algorithm, and you're going to have the algorithm pick out patterns and other things that sort of may be of interest, but you're not going to predispose it to any sort of given answer. Reinforcement learning is, again, evaluative feedback. This is where you basically reward certain behaviors in order to encourage more of that. So a good example is something like playing chess or checkers, where you can give either values to individual moves or a value to the overall goal of winning the game. And you can iterate on having the algorithm play over and over and have it try to figure out how to optimize the winning score or whatever else you've determined to be the thing that you want it to improve upon. Finally, the other thing you'll hear in this arena is deep learning. We've already kind of referred to it. And as we'll see, I'll show a little depiction later. This is pretty much in use for neural networks. And it's the idea that normally with a neural network, you have an input layer where you're putting in your data, and you have an output layer where you're outputting your answer. Well, you can sandwich a bunch of other layers in between that do various abstractions and transformations of the data. And the more, basically, when you put additional layers in between the input and the output, that then refers to the network as being deep. So instead of just being input and output, it's now deeper. It has some layers in between. That's pretty much where the term deep comes from. But again, so the characteristics for all these narrow AI examples is that they map fairly basic inputs to outputs, right? Classifying images, objects and images, looking at videos, doing the same thing. They require huge data sets for training. And although that's something that, researchers are trying to improve upon, image classification, basically the more the better. And it's often on the order of hundreds of thousands or millions of inputs necessary. And we'll talk about some of the limitations here in the next slides. And again, right, because these things are picking up on patterns, we don't have time to talk about some of the specific examples. They may pick up on patterns that you may not even be aware of that are in your data, and those could potentially cause problems. So let's see. I use this little graphic kind of as just a fun little way to depict kind of where we are on the East Coast there with things like Alexa, AlphaGo Zero, IBM Watson. We're all in the narrow AI realm. Everyone's kind of gunning for the West Coast, where entities like Lieutenant Commander Data and Rosie and K9 reside. But one of the reasons I like the little the sort of old map here is it emphasizes the idea that this is unexplored territory, and we kind of know where we're headed, But there's no one path, and there's lots of potential ways and a lot of potential risks along the way. And then, of course, it's always fun to put someone like Brainiac out in the far west. Just to, there's always kind of the threat that you hear people espouse of the worries of superintelligence and things kind of getting out of our control. But it's also important to note that machine learning is not just neural networks. Neural networks get the preponderance of the attention, but there are lots of other models for getting machines to learn from information, and you can see a list of some things there, and we just don't have time to talk about those. But for neural networks, you'll see often depictions of them like the little circles with the arrows that you've seen drawn on the left. Again, right, the first column is typically your input layer, the last column on the right is your output layer, and there's some number of layers in between that are basically processing the information and doing some sort of transformation, whether it's, you pick any sort of mathematical function or whatever else you want. And that's part of the art of this science is that tweaking those functions and tweaking the knobs of those functions, of which there could be millions of parameters, is part of what, one, makes this possible, but two, really puts, again, the art in this as people try to figure out how to optimize these systems. The graphics on the bottom right come from a really neat website that I believe OpenAI put together called Microscope, where they took some of the more well-known image classifiers and sort of visualized what some of those nodes look like. And I picked out some of the more interesting ones just to give you an indication of what some of this stuff is. It's just a fun site to go look at and explore. And that link is in the notes on for this brief. So, so here's the cheat sheet that I mentioned. So it kind of encapsulates a bunch of the stuff we just talked about, plus a bunch of other stuff I just didn't have time to talk about, such as autonomy and human-machine interaction. What I will recommend is that, above all, function supersedes terminology. And by that, I mean, try not to get wrapped around the specific terms and try to drill down to where you can talk about what it is you actually mean. That way you can maybe avoid some of the talking past each other. If someone has, a slightly different definition of what they think narrow AI is or something else, that can kind of help avoid some of the misunderstandings that sometimes happen. So what are some recent examples? Probably some of the more prominent ones are the faces that you see here on the left. And right, this is how the generation of fictional people has progressed over the course of 5 years or so, right? And we're 2 years past this example. So things have gotten just even more and more better. And I'm going to actually now talk about some of the things on the right of examples that we've seen in the last couple of years. One of my, and see, these are just some of my favorites. There are certainly hundreds of more interesting examples. On the top part of the slide there, you see this example of see-in-the-dark photo processing. These researchers basically said, hey, can we look at how to basically take photos in really low light resolution and improve the image just based on that. And the image in the middle there is what you see is sort of what was the state-of-the-art improvement for photo processing. And on the right was their result from training a network to learn how to better improve dark light photos. And one of the things I just love about this example is that, they didn't aim small, right? They picked this mylar balloon reflecting a very complicated mural of some sort. And it's just really remarkable how much improvement they were able to achieve with this. On the bottom, you probably saw this hit the news a couple years ago, but on relatively short order after the research itself was announced, which was the impressive part. So there were two pieces of information of research that came together. One was the ability to take basically 10 seconds of audio recording of a person and then being able to generate any audio clip as desired. And the second one is what you see in the lower left picture, which is basically taking a video of someone, such as Hillary Clinton, and taking a photo of, say, Barack Obama, and mapping the second face, Barack's face, onto Hillary's face, as though he were actually in the video doing the actions of the first person. And so the more famous example here was Jordan Peele in April of 2018 released this video that looked like it was Barack Obama giving a message. And as it continued on, it basically eventually revealed that it was actually Jordan Peele sitting down, saying these words, and it was using these two technologies to create this, this deep fake video, which is now, right again, is becoming a bit more of a worry, and as again, that these capabilities become more available to the average person. And then again, one of my other favorite examples is this research from MIT that basically said, let's use Wi-Fi signals that are now in the air everywhere to have detection about where people are behind walls. And so you can see the example here, the photos on the top. They're able to train an algorithm to sense perturbations in the Wi-Fi EM field and basically generate a confidence map of where that person is behind the wall. Just really, really neat stuff. Okay, we're going to talk about now some recurring themes, and I'm going to push on. So yeah, adding to AI to everything. I joke that AI is the new fairy dust, and AI is the new steak sauce. It's awesome. And it can be hard to, you know, when you see everything that's going on, to say like, well, why can't we add AI to this? And we'll talk a bit more about that. The biggest danger, to be honest, right, is using it as a fix-all or a cure-all. And so we'll caution on how to avoid, or ways to think about avoiding that approach. AI is not always better. Machine learning algorithms are not always better. And this is just one example where a researcher took, it was a time series prediction, right? You have a bunch of stuff happening over time and then, you know, predict what comes next. This researcher basically took a bunch of the state-of-the-art machine learning methods and then compared them to traditional statistical methods that have already been available. And in essence, what the chart shows is that the statistical methods were still better than the machine learning methods. So it's something to keep an eye out for. You'll occasionally see papers pop up that do this, step back and say, well, okay, we think our algorithms are so great, let's compare them to, you know, other methods that we have available. And in some cases, you see that, yeah, it's still not necessarily better than other methods that are available. I'm going to pass a little bit quickly over this one. You probably heard people talk about the black box problem. In many cases, there's very few ways to verify output, right? It just works. And AlphaGo beating Lee Sedol, the world champion at Go, is a good example of this. Where you can demonstrate very clearly it wins, and it wins frequently, but you may not be able to have a good explanation as to how it's winning. So research is looking into ways to increase transparency and being able to query and see what's going on. When things fail, they fail pretty astoundingly. And again, I'm going to actually go really fast over this one. But one of the most critical examples here is in the lower left, where you can see these kind of low resolution images, and changing one single pixel causes the image classifier to completely misclassify what is in the photo. So it's something that, you know, again, we need to be very wary of. When it looks like it's doing something and quote unquote understands what's going on, we'll find ways in which, again, there's no way a human would make a mistake, you know, like saying that one photo looks like a frog. But again, the algorithm has made a determination in a way that just has made it vulnerable to this type of change. And finally, you know, I alluded at the very beginning about these idea of dark periods. There's always kind of a looming idea of, are we going to experience another dark period, an AI winter? And, you know, here's some examples of some things that have kind of raised question marks. We'll see what happens as time goes on, right? There's a lot more research and a lot more funding being put at this in these areas, but at the same time, it's not clear how much, you know, when are we going to hit the limits of our current theories? When are we going to need sort of new theories to gap the limitations that we have today? Okay, and the last thing I want to kind of touch upon is, let me check chat here real quick to see how I'm doing. Okay, all right, we'll get to questions I think here at the end. Just some ways to think about future application of AI and AI in wargaming. So, you know, this is just my way of thinking about, like, how are people going to be using AI technology, at least in the short term? Right now, it kind of seems to break down into 4 general categories. Basically, like a completed service where, like Google Maps, where someone's already taken care of everything and you interface with it to do whatever you want. The AI is relatively invisible to you, other than it gives you what you want. There's also then maybe integratable services where maybe someone will provide something like, I don't know, a payroll module or something that, you know, you as an organization might be able to, or maybe like an email manager, you can kind of, you know, fuse this thing into your current infrastructure, right? And again, it performs a function, but you're more sort of plugging in a completed thing that performs a specific function. There's sandbox services like Amazon Web Services, where someone has provided basically all the stuff that you would need, the tools, the computation, and whatever, but you bring your own data and you build your own thing. And then there's tailored custom services, something like Project Maven or whatever, where you're gonna basically do everything custom to your specific problem. And these all kind of go in roughly increasing time, people, and resources. So also things to be thinking about is it's data. Very often we find people really not understanding what restrictions are on the data, who actually owns the data that they maybe think they own. Even some questions will come out, you know, can you analyze that data on an exterior system if you're going to use Amazon Web Services or one of the AWSs that, you know, isn't a government approved one or whatever. Do you have enough data? How complete is it, et cetera? The data ends up being probably the biggest issue. And it also importantly, it still takes time. C-SPAN said a year or so ago that they used AWS to create a database for identifying almost 100,000 politicians. All they reported was it took 3 weeks to build. They didn't say how many people were involved, et cetera. But, you know, that seems like a relatively straightforward task. But again, right, it takes time and to clean the data, to make sure it's functioning properly and doing all that stuff. So time and time again with surveys and whatnot, they all come back with the data gathering, cleaning, and preparation have been the biggest time sinks. And then finally, some thoughts about thinking about AI in wargaming. And this is about AI in wargaming, not using AI to wargame, more along the lines of if you're sitting in a game and someone wants to add AI to something, or if someone raises the question of how can we use AI to solve a particular problem, or can it? First and foremost, I'll state the obvious and say, you know, get an AI expert or someone familiar with the state of AI research to help assess the feasibility or difficulty of the idea. But barring that, I sort of threw down a very basic hierarchy for thinking about using AI. And it's a very similar hierarchy for ideas and innovation itself. And I'm going to start at the bottom of the 3 bullets, but basically the easiest ones to think about are doing what you do now, but better, faster, cheaper, et cetera. It's typically an optimization problem, you know, stocking a warehouse more efficiently. A little bit harder than that are doing new things, but maybe not too different from today, sort of simple evolution of what's going on. So again, stores without cashiers, right? Amazon is piloting these cashierless stores, but puts together a bunch of things that are all kind of available today, but thinking about things a little bit differently than what we do now. But then at the top, the hardest ones to really think about and about how to get there are the things that you only dreamed were possible, or maybe never even dreamed were possible. The leap evolutions, something like robots running both the warehouse and the delivery, right? So there are people, I'm sure, that are aiming towards those types of goals, but those are much harder to achieve and are going to require, many years more work and research. And so again, when you're in a war game and someone says, "Hey, let's add AI to this," it'll help, I think, if you sort of be specific about the actual capability or effect that you're looking. So focus on the task and not the AI. Are you trying to optimize an action or situation, better decision? Are you taking some sort of action again? Are you trying to replace a human function? Again, maybe to make it faster or more accurate or whatever. Be more specific about what it is you're trying to do and the effect you're trying to achieve. Now, ideally, you'd have a more detailed taxonomy to help with that, but it turns out nothing really quite satisfying exists out there. One of my colleagues is currently working on something, but it is still a couple months in the making. So perhaps check back in a month or two to see how we're progressing on that, to help people sort of connect the dots between things you might want to do and how you might get there. If you've identified the capability and the effect, then figure out what data is necessary to achieve it. And do not assume that someone out there has your data. It's worth actually tracking it down. If you find out that it's not there, then maybe you just generated a requirement if you really want to get this thing done. You also need to, unfortunately, assess the availability and the state of the data. Again, do not assume that it's easy to get or that it's even complete. I can't tell you how many times, even just in normal research, where someone says they have a database and you get it and the thing is maybe 30% complete with holes everywhere. It's just that unfortunately raises its head a fair amount. And then again, compare that idea, that capability or effect, to other research. Is it something that's you can point to that's been reported in the literature, that's been done before, that's a bit more favorable about enacting your idea? Or is it something that is far-flung or perhaps like a DARPA program or something that is going to be a lot harder to enact? And again, this is where maybe an AI expert or someone familiar with the field can help you figure that out. Okay, and the last slide, and we've been screaming through this, so the resources. There's lots of amazing and free resources on the internet that are available. I've listed just a tiny fraction of them here. Most of them are books. That first site is a really neat interactive website on exploring complexity. Lots of neat little things that you can play with and see things fly across the screen and change as you change the knobs. And then, of course, I have to plug my own thing, which is we have a weekly podcast here at CNA where I and my colleague Andy Lachinsky sit down and talk about the latest and greatest stuff going on in AI research. We have more of a focus on military implications and whatever. So we'll be talking about things that Department of Defense are doing, and not just Google and DeepMind, although we talk about all that stuff too. So anyway, wow, that was really fast, and I really pushed the time limit here anyway. So happy to take questions at this point.
Thanks so much, David, and that was a great presentation. And now we'll go over to Mark to handle the Q&A.
Thank you, Dr. Wong. Dr. Broyles, thank you very much for the presentation. We've got a fair number of questions in chat in the 9 minutes we have left, so I'm just going to start top to bottom in the order received, if that's okay with you.
Yeah, go for it.
All right. First question is from Dr. John Hanley, and the question is, I'm just going to read them verbatim, is, what theory for rational action do these techniques use other than game theory?
What theory other than rational? I'm not quite sure I actually understand that question.
Okay. I think he's asking, when you talk about different techniques, are there any techniques that your theory uses? I guess there are any disciplines beside game theory that come into play?
As far as I understand, right, the determination of rational action is the reward function or whatever is programmed into these things. So I think you would have to derive your idea of rational action from the reward function you put in. So it in fact is why sometimes you see almost irrational action, right? There have been examples of, stories where researchers have tried to get, an AI to be able to land an air, do air flight or other things. And what was the one example where the AI basically determined it could achieve a 100% success in landing a plane by slamming the plane into the ground with a high force, because that caused an overflow in the code that basically caused the thing to crash, but it resulted in a 100% success rate, right? So you get an irrational action even though you thought you had determined a proper reward function. But that's the thing to keep in mind here is there is no right. It's that level of simplicity at this point. There is no other way to define something like a rational action, unless if you're codifying it into some mathematical equation.
Thank you. So the next question we have is from Mike Dunn, and I'll read. I think of the horrible direction Microsoft's Tay Twitter bot had taken with its machine learning the wrong lessons. Can you talk about what is being done to mitigate bad machine learning?
Yeah, honestly, I think this is one of those we're learning as people discover things. So if you're not familiar, right, Microsoft put this Tay chatbot on Twitter, and within a few hours, Twitter had turned it into a racist and horrible spewing thing. And yeah, they've learned a lot at this point about how not to let that happen. But even just recently, researchers see that what was the some researchers came out with this technique that can increase the resolution of a photo. So let's say you have a kind of a blurry photo or one that's just at a lower resolution. You could have it basically create a much higher definition picture of a person that it could be. It's not that you're saying that it is that person, but it's finding a high resolution face that could match that blurry photo that you had. Well, people discovered very quickly that you could give a photo of a person of color or of another ethnic group, and it would turn the person into a white person. And there were, so the researchers again hadn't really looked at. They didn't realize that was a problem with the system that they had designed. And again, in large part, that happened because the images that they were training on were skewed in the racial representation of what they had trained it on. So researchers kind of find things like that as they're happening, and then they go back to the drawing board, so to speak, and figure out how to do better next time.
Thank you very much. The next question is from Guy Parker, and it says, might there be a moment to discuss the hybrid AI plus human system versus a pure AI system? Excuse me. I read that in the chess game context, the hybrid generally defeats pure AI. Thank you.
Yes, thank you, Gary. That is actually on my cheat sheet. It's, I think, the very last entry where I talk about human centaur systems is what they're sometimes referred to. And the great example there is Gary Kasparov, who basically, after being defeated at chess, teamed up with an AI and was able to, in combination, beat the AI that beat him. And so the idea of the hybrid, or again sometimes called centaur, is pretty popular, and you'll see a fair amount of work being done in that area.
And then perhaps time for one more question. We have James Snyder, who asks, are the hidden layers in deep learning an analog to human memory, or are we still steps away from having AI learn from the memory of previous actions and outcomes?
No, it's a good question. I think, the whole concept of neural networks was a way to kind of mimic how we in a very simplistic way about how we think, neurons interact in the brain. And it's something that you see very actively, which is neuroscience feeding information into machine learning AI research and vice versa. It's not quite clear at this point how, well, to be honest, right, we still don't understand how human intelligence works. So it's really difficult to know at this point whether the abstraction that's happening in neural networks, deep layers, how that works in analogy potentially to the way the human brain works. But there are attempts to do the last part of your question, which is ways to include what's been called lifelong learning, or to have a memory of those previous actions and outcomes. And it actually requires different approaches than just tinkering with a neural network. So if you ever look into, again, things like lifelong learning, or I forget what the other term is, there are different ways to look at how to help an algorithm have a retention of its previous stuff that it's done.
And in the brief time we have remaining, various participants have asked, would you be willing to share your slides? Could you speak to that, please?
Oh yeah, no, absolutely. These slides, and again, the notes are filled out with even more details and links. I think I was told the Connections is putting this on a repository somewhere. If not, feel free to drop me an email as well. Unfortunately, it's 15 megabytes, so hopefully it doesn't, destroy pipelines.
And then if you would, Dr. Broyles, we have about 1 minute. So a last question from John Hanley. Could you tell us about Project Maven?
I wish I could. I do not have a lot of insight into that, into what they've been doing, other than work mostly on image classification on video feeds. But I don't have any insight more than that, unfortunately.
Great. Well, thank you again very much, Dr. Broyles, for the presentation. Greatly appreciate it. And
right.
For all the participants, the conference will reconvene at 13:15 Eastern time, wherever that puts you in the world. So thank you again very much.